Okay, we're going to get started. I don't know why people aren't coming to class, but I'm going to start cracking their skulls. Actually, I might just do a quick go through of the cards, set theirs aside, and get on to the next thing.
You could go into the lounge and yell at the people who are...
They are still in there.
Yeah.
They are?
I think they're studying for thermal.
Right? Question mark?
Let's go. Everybody, come on, let's go.
Are you saying?
Let's go. I feel like nobody in there.
Madison is the nerd.
Come on, come on. Let's go.
Absolute nerd. We're gonna particle in the lounge space and keep more seats in there.
Where are they? In the computer lounge or in the lounge lounge?
Particle in the lounge. We can check both.
We just have class in here.
All right, I just want you to point them out to me, and I'm gonna. Who we got?
Hey.
Why aren't you in class? Why aren't you in class? Get your butt to class.
I said there was a 20% chance you'd actually get it.
Get your butts to class now. Go. Go. Go to class. Go to class.
Come on, Brad.
Hold on, we gotta check this room. Nope, we're good. We're good. All right, come on. Let's go. You don't mess around with me. Hey, I got a packet of quizzes for you to grade. I'll tell you. It's a beautiful building, though, isn't it? It's a gorgeous building. I'll do it. I'll put you on the interweb. It's a wintry day. Okay, come on. Hustle back, kids, and stop performing for YouTube. You've got to go to class. You've got to learn important stuff. Thank you, soldiers. That was most beneficial. I don't think we could have gotten them to come if it had just been me. Okay. All right. Now all I'm going to say is there's one person in the room who can interpret my t-shirt. And I'll just let you figure out who it is.
But you're wearing a jacket.
No, I'm taking it off.
I think it's Madison.
I could send that to everyone.
Oh wait,
No.
is that the
video?
Oh no, I hate that video.
No. The story is way deeper. See, this is a lyric from a song, which is part of a 5-song opera, which was written between me and Brian Wecht and Brookie Williams. How many of you know who Brian Wecht is? Ninja Brian, who is in town visiting me right now.
What?
Yes.
Yeah, can he come?
I know Ninja Brian. But anyway, so we're going to get done at 6:15 so I can head up to Boulder and have dinner.
I have that album if anyone wants to make.
Anyway, back to physics. But we got to make sure the picture gets on there. Okay, let's go. All right, so we're going to do a quick recap of E&M because today we're going to talk about SU3 and the strong interactions. We're going to skip the weak interactions for now because in a very detailed sense, QCD or the strong interactions are just a much simpler generalization of E&M than the weak interactions are. The weak interactions have so many things wrong with them. It's a real mess. We're going to talk about it, but we're just going to go ahead and step up to QCD. And one of the interesting things about this class and what we're going to talk about today is, you think about electromagnetism, and one of your initial reactions is that electromagnetism kind of governs everything, right? It governs light, but it also governs atomic and molecular bonds, and it's what drives circuits and everything. And then if I ask you, what does the strong interactions do? What's your answer?
symmetry thing.
Is that a nuclear?
Well, it's a nuclear thing. It's, yeah, kind of, possibly. So is electromagnetism, by the way, but, you know, kind of, sort of. Yeah, so the strong interactions seem to play a vastly different role in our universe than electromagnetism. So that might lead you to believe that if I wanted to formulate the theory of electromagnetic interactions and then the theory of the strong interactions, that they would be formulated in very different ways because the output is very different. It turns out that they are formulated in identical ways. Okay? There's just one very significant difference between the underlying formulation of the strong interactions and the underlying formulations of the electromagnetic interactions, which gives rise to all the difference. And that's the fact that the strong interactions are based on a non-abelian gauge group. The elements don't commute. And we'll see that in our formulation today. Okay, but we're basically going to be repeating what we did for E and M, so I'll very quickly review that for you. So for E and M, we had the Lagrangian h bar c psi bar gamma mu d mu psi plus I q h bar c psi bar gamma mu a mu psi plus mc squared psi bar psi plus 1 over 16 pi, and I'm writing this small up in the edge because we're going to keep it. Where f mu nu is of course given by d mu a nu minus d mu a mu, but we later at the end of the last class found that this could also be written as 1 over iq times the commutator of the covariant derivative, which we defined in the following sense. Okay? And then we found that this was invariant under a local U1 transformation, so the Lagrangian here is invariant. If you do the transformations I'm about to write, you put them into the Lagrangian, you end up with the exact same thing you started with. And this is if you send psi to psi prime, which is e to the iq phi of x mu, where phi of x mu is a parameter governing the transformation, but it varies over space-time, and that's why I would call this a local transformation. And a mu goes to a mu prime equals a mu minus d mu phi of x. Okay? Now, if you didn't leave the last lecture completely comfortable with this result, that's fine. That's part of the joy of doing what we're about to do. We're going to basically repeat the whole thing, except at a more sophisticated level. But we are going to have a lot of the steps that result in very similar outcomes. So, any questions about what we did with E and M? Is everybody comfortable? My markers aren't working again today, damn it. Crap. Okay. Let me see. All right. So, okay, so what about the strong interactions? So for the strong interactions, are based on a local SU3 invariance. Okay? And it acts only on quarks. Now, if we are going to start with a matter Lagrangian, like we did for QED, quantum electrodynamics, Jalon, will you tell me what type of Lagrangian, free Lagrangian should we start with before we gauge the symmetry and introduce the interactions?
I guess this is the matter one.
Well, they could all have matter.
Yeah.
You got a hand up in the front row if you
Yes,
want.
sir, go for it.
Is it the L1/2 referendums?
Yeah, it's the Dirac Lagrangian. Okay, it's L1/2. Okay. Now, that L, of course, looks like this. And we noticed, and psi bar here is defined as I psi dagger gamma 0. Now, you might or might not remember that when we did this with electromagnetism or QED, this is the basic theory of QED, we didn't have to introduce anything new when we wrote down this Lagrangian because we're acting on complex spinor states with complex numbers. So if you have a complex spinor, the spinor has 4 components and they're all complex, you can hit that with a complex number and you don't have to add any additional mathematical structure to it. However, what is the dimensionality of the matrices we anticipate dealing with in SU3? SU3. What is the dimensionality of the matrices that we we'll ask a person. Joshua. Wait your butt. That one.
Can you repeat the question?
What dimension of matrices do we expect to work with in dealing with SU3? 3 by 3 matrices. Yeah, so this is my question. A spinor has 4 components. These are all sized. How am I going to act on that with a 3 by 3 matrix? Well, let me ask you a question. What do these 4 components represent? Like, what kinds of transformations with 4 by 4 matrices do you do on the components of this spinor? Well, you already got your question, so I'll ask somebody else. It's not here anymore. Who is that here? Wow, we're losing people left and right. Hunter. Ian. Yes, there you are. Thankfully. So when we use 4 by 4 matrices to act on this spinor, what were those 4 by 4 matrices representing and doing? What were they responsible for?
This may have been last week when I wasn't here, but is that like a Lorentz transformation?
Yeah. The 4 by 4 matrices that you would hit this with would be enacting Lorentz transformations or rotations. They would not be the standard 4 by 4 matrices that act on vectors. You know how to write down the Lorentz transformation as it acts on a vector and the rotation matrix that acts on a vector. They would be spinorial representations of them, but that's what those 4 by 4 matrices would represent. They would, if they acted on this and mixed up these components, they're mixing them up in a manner that rotations or boosts would do, okay? I'm going to tell you this. This set of transformations does not touch space-time. So these things are going to be 3 by 3 matrices that don't act on space-time. So the fact that there's 4 components here doesn't mean shit. So we need how big of a thing for 3 by 3 matrices to make sense in their action. It has to have how many components? 3. Where are those 3 components going to come from?
Alex, get in here.
Where are they coming from?
clear size 3-component vectors.
But what are the 3 components of those vectors?
Color. Color.
Yes, it's color, okay? So in order to do QCD, what we have to do is we have to take these spinners and we have to blow them up into 3-component objects. Where each component is labeled by a color, red, blue, or green. Yes?
So is this the same spinner or is it a different set of spinners?
It's the same spinner, but it's being blown up into even more degrees of freedom because each of these size is a 4-component spinner. The 4 components are just the space-time properties, okay? So just to give you an idea, if I labeled each of these by a letter A, then each of these would carry an A. Would each of these carry an A? No. Okay? But each of these are 4-component spinners in terms of space-time, but we're giving it an additional set of components in an imaginary internal space. It's called color space. And color space you can really think of as just, something like that. So this thing is a vector in color space, but each component of it is a spinner in space-time. Yes?
There's nothing like color is just the way we choose to sort of represent it, right? There's nothing like physically.
Colorful?
Yeah.
No,
Okay.
not at all. Yeah, so that's a big problem is you've got to label 3 things. You might ask yourself, well, in electromagnetism, we've got positive and negative charge. So that's 2 things. So why don't you label it as positive charge, 0 charge, and negative charge? And then call that your 3 dimensions. Okay? There are 2 problems with that. Number 1, positive charge, 0 charge, and negative charge, that's not shit. 0 is a linear combination of positive and negative, so it's not an orthogonal vector. But it's worse than that, and this is a very important note, which you just take in, you'll digest eventually. When I say that you have positive and negative electric charge, I'm talking about different values of a given charge, electric charge. Things take different values of electric charge, okay? We can refer to these colors as charges. In fact, that's the way they're thought of and the way they're worked with mathematically. However, here's the difference. Red, blue, and green are not different values of a single charge. They are 3 different charges. And each of them can take multiple values. In fact, they really only take 2. They are either red or red bar, which is associated with antiparticles, green or green bar, or blue bar. Okay? So if you think about it, there's a sense in which this is like bumping electromagnetism up to a theory with 3 different kinds of charge. And what that means is that you have to represent a matter state by its components along those 3 different charge directions. You only need 1 when you're doing E&M because there's only 1 charge. So one of these spinners does it for E&M. But they have to have 3 components in color space. Is this kind of, yeah.
So why is it that we're trying to have an SU3 matrix act on the spinner? Why SU3?
That's a really interesting question. So the history of particle physics is something that you should definitely learn after you understand particle physics. Because if you go back and you try and trace and learn particle physics by tracking through its history, it's a nightmare, okay? It's much more elegant to just accept that SU3 is going to create interactions for us, and those interactions reproduce all of the results that are seen in an experiment, okay? And then you can go back and kind of piece together how they figured out that it was SU3, and that's a really long and complicated story. It's to do with Murray Gell-Mann's eightfold way kind of weirdness. But anyway, I don't want to go there. So I'm going to feed you that the standard model is based on an SU3 cross SU2 cross U1 local symmetry groups, and that explains all of the forces in the standard model. How they piece that together is a longer story. Okay? But we're going to just take SU3 as our starting point and bang it through this machinery and see what differences came out. Okay? Okay. All right. So as you can probably imagine, this Lagrangian is invariant under a transformation of the following form. Oh, and I should argue that this transpose includes color space. So the transpose here, because psi involves spinors, but it's a set of spinors. When you transpose and you want to form this sort of horizontal thing that you can combine with this vertical thing, you got to transpose everything. But it's not really that important at this moment. Okay, so this Lagrangian is invariant under this transformation, where, of course, there's a similar psi bar transformation that we have here. We can just write this in terms of the same thing. This is a global transformation because I've just written phi without being a function of space-time. So this is the global version. This is the one which the Lagrangian you start with is invariant under, and then you have to massage it and do some work on it to make it invariant under the local form of this, which is what we're going to do. But just to sort of lay out what this is, if we compare to a transformation in gauge theory in general, where GA is the vector of matrix generators, and VA is a vector of parameters. Okay? In the U1 case, which is what underlies electromagnetism, both GA and VA only have one component. So you just call them numbers and functions. Okay? But here we have to remember that when you have multiple generators in your group, and SU3 has 8, when you have multiple generators in your group and you want to write a transformation, you sum over all of the generators, each with its own transformation parameter. So this is like writing down a three-dimensional rotation. You sum over the 3 generators of rotations, and each of them get their own angle. Here we've got 8 generators, and each of them are going to get their own parameter. Okay, so we can say that comparing these two, lambda here is playing the role of the matrix of generators, and there are 8 generators. And the phi is going to play the role of the 8 parameters. One for each generator. Okay? And if you don't remember, you should go back and review how it is we came up with the fact that SU3 has 8 generators. That's a highly non-trivial calculation that you have to do. Well, not highly non-trivial. It's not that bad. But anyway, go ahead, Nancy.
So in this equation, you're saying that this is a sort of space of charges. So what does Q mean in this context?
Yes. Very, very, that's exactly what I'm about to write down. Thank you. That's an excellent question. So minus Q over H bar C is going to play the role of, minus G, which I don't have written in here for some stupid reason. But anyway, so G is going to play the same role, but it's going to be given a different name than Q in U1 when you're doing SU3. So the idea is that in electromagnetism, there is a parameter Q, which is the charge, you know, the fundamental electron charge. This is also the measure of the coupling strength between the electron field and the photon field. Okay? All right? Now you can come over here and say we've got 3 different charges. Do we have 3 different couplings? Because here charge played the role of coupling. And there was, you know, one coupling, one charge, obviously paired up. Here we have 3 different charges, so do we have 3 different couplings in the field? Or 3 different couplings between the gauge fields and the matter fields, which will play out in the details? And the answer to that is no, because if the coupling strengths were different, there's no way this would be invariant under SU3 rotations, which mix the charges together. Does that make sense? So you have to have the couplings associated with these charges. That is, how strongly does the gauge field couple to the matter field? The couplings have to be the same. Okay? So, yeah, so I think that answers your question. Okay, so, all right, now we are in a position to try and localize this thing. So let's see if we can do it. All right, so we're going to try and fly as we did with U1. So for local, we know that we're going to basically, oh Lord, let me write it down correctly. We're going to promote the parameter vector phi into a set of parameter functions, okay? And before we cram this into this Lagrangian and start demanding that the Lagrangian be invariant, we're going to reflect back on some sort of insight that I gave you towards the end of the last lecture on what exactly were we trying to accomplish in needing this Lagrangian so that it would be invariant. And you might or might not remember, but what we ended up discovering was that we made a new derivative so that when we transform the derivative itself transforms and the field transforms. This thing actually transformed like this. It is not obvious that this happens. And it won't happen with this Lagrangian. You have to modify things. But, you know, you might or might not remember, but back when we first localized the Lagrangian and we just transformed this piece, the derivative acted on this and on this. And so you created 2 pieces out of 1. There's no way that was going to be invariant. So we had to add in the gauge field, et cetera, et cetera. But at the end of the day, what we discovered is that this had to change into this had to change into this, but those changes combined became just an overall operator acting on the original derivative d mu phi, okay, or d mu psi. Because, of course, why do we want this? We'll look at the Lagrangian. It's d mu psi, so imagine if you make this a capital D, which we'll do. So this is capital D mu psi, and you do the transformation. If d mu psi ends up with a whole factor out front, then that cancels the factor that you get from psi bar. Remember, psi bar just gets this factor on the right. So can you spot it? Like, this Lagrangian is clearly going to be invariant as long as my derivative does this. And the MC squared term is automatically invariant because psi bar and psi automatically get terms which cancel each other. Okay? So I'm saying this because this is the criterion I'm going to use to figure out how A has to transform. So are we all comfortable? Okay, all right. So here we go. So let's see. So d mu psi is going to be d mu psi plus ig lambda dot a mu psi.
Hey, Florida.
Huh?
Sorry, I hope it's not going back too far.
Yeah.
But the invariant that you were talking about, the two exponents both have negatives, right? So they wouldn't cancel? I'm confused on that. Right, your psi transformation and your d mu.
Oh, hold on a second.
Oh, wait, or is psi bar is the opposite sign, right? I think you just.
Yeah, you're right.
Okay, sorry.
This should be minus and this should be plus.
Okay.
You're right.
Thanks.
Sorry. Thanks for correcting me on that. I think I had it written wrong in my notes, so I just copied it down wrong. Okay, so first of all, I have to introduce our new derivative. And this looks a lot like the derivative that we're using up here. So it's just an inspired guess at the form the derivative needs to take. Except, of course, I mean, we've got ig, that's playing the role of iq. It's acting on psi, so if you let this act on psi, you'll get a psi on the right. But here's the weirdness. Here there's an a mu, and here there's a lambda dot a mu. Okay? What is lambda dot a mu? What are the lambdas? It's the set of 8 generators of SU3. They're matrices. It's dotted into a mu. How many a mu's are there?
8.
There are 8. Lambda is an 8-component vector. Each of its components are matrices. Okay? If it's dotted into a mu, this is the dotting here means of the 8-component part of this. So we're introducing 8 gauge fields. What role did the gauge field a mu that we introduced in electromagnetism play? Like what particle did that end up describing? The photon. So what particles do you think these 8 gauge fields are going to end up describing? The gluons. Gluons are the particles which mediate the strong interaction force between matter particles. Madison.
So a few index would normally indicate like a space-timey thing. Does it not here?
It does. No. This is, okay, I am very sorry, but this is the way this shit goes. Yeah, this is a 4-component space-time dual vector because the space-time index is lower, okay? If it were upper, it'd be a vector. So this has 4 components in space-time, which is how you transform it under rotations and Lorentz and so forth. However, there are 8 of them which form an 8-component.
Vector of dual vectors?
Yeah, but each of the 8 components are dual vectors.
Yeah.
So you really don't want to ever write these things down explicitly because you've got to write down 8 4-component vectors, dual vectors. Okay? And you don't ever want to dot them with this because you're combining each of them with a 4x4 matrix. Jesus. Yeah, it gets pretty crazy. That's why we need this super condensed notation because we don't ever want to write this out in full matrix form. It's really horrible.
Would there be like a tensorial way to write that?
This is, well, yes. And I actually will introduce an index to label these things in a few minutes. Okay? All right?
I don't like.
Okay. You got just bear with me. Bear with me. It'll be all right. Okay, so we're going to transform this into d mu prime psi prime. Okay? So we know that in this term, you just transform the psi prime. You don't transform the partial derivative. That's just a partial derivative. It doesn't go anywhere. I mean, it's going to screw things up when I put in the transformation that acts on psi to make psi prime, but we'll see that that's corrected in a moment. And then we have IG lambda dot A mu prime psi prime. Okay? All right, so we can plug in e to the minus IG lambda dot phi of x mu psi plus IG lambda dot A mu prime e to the minus IG lambda dot phi x mu psi. So all I've done is I've plugged in the transformations of the two psis. Okay? And then we've got to act with this derivative on both of these. So we know what that's going to give us. It's going to give us d mu e to the minus IG lambda dot phi. And phi is a function of space-time. I'm just going to leave that out. Okay, now what we want this to be equal to is this. That is, we want it to be equal to e to the minus g lambda dot phi times the original derivative, which is this. Okay? So what I want is I want this line to be equal to that line. What do I have the freedom of specifying that makes this line reduced to this line? A mu prime. That is, we haven't said how A transforms yet. And so we pick the transformation of A so that this line becomes this line. Now, before I write down what that takes, it doesn't take much. Remember, obtaining this for how our derivative transforms is basically this right here. It's saying the derivative on a psi just transforms with an overall e to the minus g. This will guarantee that your Lagrangian, written in terms of capital D, is invariant, because the capital D psi will get an overall factor of this, psi bar will get the positive, those will cancel, the two will cancel from there, this Lagrangian is invariant. Okay, so I'm not plugging everything into the Lagrangian, expanding it all, and mopping up the floor. I'm just checking out the derivative. Okay? So what we need for the transformation of A is that lambda dot A mu prime is e to the minus IG lambda dot phi, lambda dot A mu, e to the IG lambda dot phi, plus I over g d mu e to the minus IG lambda dot phi times e to the IG lambda dot phi. It's kind of interesting, right? Does that look anything like this? No, it doesn't. Why? Tell me why. Daniel here? Oh, that was fun. The stable punk. Would anyone like to ask me a question? Yeah.
Why are they different?
Why are they different? Well, if I squint my eyes for just a moment, and I said, are you going to pay attention? Why you got your nose in your notebook? Pay attention, Avery. If I could freely move this exponential over here, it would just hop the fence and cancel with this exponential, leaving me lambda dot a mu, which is kind of like the first term over here. There's that lambda thing, but we won't worry about that right now. And then if I took the derivative of this, I would end up with a d mu phi times this thing, which would cancel this, and that would kind of generate this term. So if I could just move this past this, so that it could cancel this, and take this derivative and let this exponential, then it would reduce to this. But why can't I do that? Because why? It's non-abelian. What is a lambda there? It's a matrix, it's a generator. What is the lambda there? It's a generator. What about the lambda there? Yeah, these things don't commute. I mean, you can move them past them, but then you have to pick up the result of the commutator. Okay? And similarly here. So if you start with this, which is true in general, and you say, I'm going to work with an abelian group, which is certainly the case here, then you can just move this over, cancel this, and you're done. Okay? But this is the more generally correct thing, which is valid for a non-abelian transformation law. Okay? So it's a bigger picture. What we're doing, and I should be clear about this, what we're doing is going to completely include electromagnetism. It's a part of this story. In fact, to get electromagnetism out of this story, all you have to do is say, I'm going to set blue and green colors to non-existent so that I only have one color, red, and that's going to give you electromagnetism with a color called red instead of electric charge. But who cares? Okay? So, let's see. Now, yes, so here's an interesting observation. We are going to take the Lagrangian and we're going to replace the partial derivative with this new covariant derivative. Okay? That term is going to end up with something which takes the form psi bar lambda dot a mu times psi, right? Plus some coefficients. What is this describing? This is the interaction. This is the quantum chromodynamic, or the color interaction between this field that we start with, psi, that started out as a free field with no interactions, and the gauge fields that we had to introduce to localize this SU3 symmetry. So this is going back to, you know, the amazing element here, which is that demanding this local symmetry hold forces us to the interactions. This is where interactions come from in the standard model. They all come from these localized symmetries. Okay? However, SU3 is going to be richer than this. I know. Just wait. All right, so after we fix the derivative, in electromagnetism to be covariant by introducing this gauge field A, what did we then do for A? Does anybody remember? I said after we had introduced this field A, to redefine the derivative, I said A is currently a background. That is, you have to tell me what the configuration of A is, and then I can do physics. But I would really, really love for A to be dynamical. What did I have to give A? I had to give it a kinetic energy term. That's what this is. So similarly, we've introduced these gluon fields, these gauge fields, the 8 A mus, But right now, because all we've changed is the derivative here, okay? Because right now our theory is just this. With this theory in hand, these gauge fields are background fields. We really want to allow them to propagate. We want them to be dynamical parts of the theory, so we need to give them a kinetic term. Okay? What kinetic term do you think we should give these things? Well, which Lagrangian kinetic term was this? Yeah, this is the Proca term. Okay? And I'm going to go ahead and grab a result from last week, which is the Proca Lagrangian, which is this, plus a mass term for the A. You can't give A a mass, because the mass for A term is not going to be invariant. That's the same for U1. It's going to be the same for non-abelian group. So what we can do is we can just add a kinetic term, okay? And now this Lagrangian is going to have the interactions between the gauge field and the matter fields here. This is an energy term associated with just the particles having mass. This is the kinetic term associated with the gauge fields. Okay? However, what does F mu nu look like? Yeah. F mu nu, we can use one of two definitions. We can either use this definition or this definition. It turns out this is the definition we must use. And for a non-abelian theory, it's going to give us a result which is very different from this. But it's going to contain something exciting. So I'm going to bust through it. It's going to be a little gory, okay? But you can work with it. All right. So I'm going to get rid of this. Probably going to try and maintain that, but I don't know. We'll see. And let me, oh dear God, this is huge. Okay, yeah, we'll do it. Okay, so, yeah, we can do it. Okay, so I'm going to try and evaluate minus IG d mu d nu acting on psi. Okay, these are operators, so to evaluate their commutator, you have to let them act on something, because that's when you actually get the business of what these things are doing. But at the end of the day, the expression on the right-hand side is going to have an overall psi at the end. So then you just cancel off your psi's and you say this is what the commutator of this is. Because you just want the commutator d mu d nu. You don't want it acting on psi, because this is just the derivative of A. Okay? So here we go. We've got our covariant derivative. We had it right here. I just erased the damn thing. Yeah, so covariant derivative is d mu plus IG lambda dot A mu. Okay? And here we go. That's pretty straightforward. I'm just writing down the definition of the commutator. And now we'll act on everything with this. What is so damn funny? Does anybody have a joke while I write this up here? Never mind.
A horse walks into a bar. The horse says, or the bartender says, "Hey." The horse says, "Yes, please."
That's pretty funny.
I don't get it. Let me see. The horse. Oh, the horse.
That's a real question.
What do you get when you cross a horse with a donkey? A honky.
You write faster. I gotta get this shit done. I can't hear any more of these horrible jokes. No, I'm just kidding. That was marginally funny, Avery.
Thank you.
But I'm done. Okay. Okay, so literally, folks, I mean, this is just the commutator of the derivatives. This is with mu and nu, and this is with nu and mu. Okay? And they've got a relative minus sign. There's a minus sign up here. Okay? The first line and the second line I kept distinct because in the first line we might notice, hey, look, I can always swap partial derivatives, so these two cancel. Lambda dot a nu a mu. Ooh, lambda dot a nu a mu, or d mu. So the first line cancels, and what I'm left with is the second line.
Wait, what just canceled? Why did stuff just cancel?
I can always swap the order of partial derivatives. So I can turn this term into this term, but there's an opposite sign. This term and this term are identical with opposite signs, and this term and this term are identical with opposite signs. Okay? And then I can clean up what we've got here and write it in the following form. D mu lambda dot a nu, well, not this. So this is going to be minus I over g d mu d nu, where I'm going to drop the psi on the far right of everything. Drop the psi here, drop the psi there. Minus d nu lambda dot a mu plus I g times the commutator of lambda dot a mu with lambda dot a nu. I really and truthfully, all I did was I plugged in this definition for d mu into this commutator. That's what these terms are. The one on the right acts on psi. That's why the thing on the right is acting on psi, but who cares? Okay? And then I multiplied all this out. All right? I canceled out various things. And this is what I'm left with. All right? Now, we're almost there with some goodness. First of all, I want to rewrite something mildly. So let me write lambda dot a, and this was satisfying your need for this. Let me write lambda dot a with an index, and this index is running over what values? Say it again?
1 to 8.
1 to 8. It's not running over the colors. There are 8 generators, 8 gauge fields. So A is just an index over the number of generators. This is another complication, you know, when you come from the U1 story where there's one of everything. Okay? So this is a vector, an 8-component vector of dual vectors. An 8-component vector of generator matrices. Okay? So we're going to write a lambda dot a that way, or we can write it as lambda b a b. Okay? And the reason we're going to do that is because now, remember this is f mu nu. That's the reason we're constructing this thing. So f mu nu is given by this expression. Don't look at that. Okay, so f mu nu is given by this. So I can now say that f mu nu by, all right. So now I can say that f mu nu is given by So if I literally come in here and where I see lambda dot a nu, I write this as lambda a nu. Lambda dot a nu, lambda a mu. Lambda dot a nu, lambda dot a nu, lambda b dot b nu, because I don't want a's, 4 a's in here. Then this is going to take the following form. I mean, notice that this is just lambda a nu, which is what that is, using this substitution. And then lambda a b a mu is this one. And then for these, I'm just using different letters. I mean, you can use any letters you want as long as they're summed over in pairs. Yeah?
Is there a reason we're not writing that, like, parentheses term as a commutator? Because it is.
What parenthesis term?
Like the du a nu, isn't that kind of the commutator type of thing?
Well, just
Is
hold
that
on,
a little
hold on. I mean, look, hold on. No, it's not the commutator. Okay,
Well,
yeah.
You could write it in that, like, form. I don't know.
No. You can write it like that, but you have to write it like this.
Yeah.
Because you're just commuting the indices, you're not commuting B with A. That's very different.
Yeah.
So yeah, you can write this like that. Okay? But, you don't really need to. But here's the nice part. Look. This term looks a hell of a lot like that term. So you get the standard derivative term that you use in the field strength of abelian theory, but of course you get 8 of them, and these 8 terms are dotted into the 8 generator matrices. But this is new. Now, you might or might not recall, because I think you forgot, but in homework 3, you worked with this. This is the Lie algebra of SU3. The Lie algebra of SU3 is given by GI, GJ is IF, IJ, K, GK, where these are the structure constants of SU3. And they're not the same as the Levi-Civita symbol that we use for SU2. I gave you all of them on the homework sheet. Okay, so there's a lot of them that are 0, some of them have weird values or whatever, but nonetheless, that's what this term is replaced by. Okay? So just relabeling this, since we're calling the generators lambda instead of G, so we can write that lambda B, lambda C is I, F, B, C, I, F, A, B, C, lambda A. And yes, okay. So at the end of the day, this term is going to come out to be lambda A d mu A nu minus d mu A nu minus G F A B C lambda A mu B A nu C. Now, you might be like, oh, you replace the commutator. who cares, you know? But actually, there's something really nice about that final expression that was not present in this expression or this expression. What is it? Well, let me ask you, when you're looking at this expression, is it possible to pull out an overall lambda A? No. What about this expression? Yeah. There's a lambda A there and a lambda A there. Those are the only two generator matrices. So you can actually pull this lambda A past all this stuff. It commutes with everything. We follow? Okay, so another way to write F mu nu is as lambda A times FA mu nu, where this and this and this all combine to give me F mu nu A. Okay? So it turns out that the field strength itself breaks down into a vector. That was not obvious because the field strength contains these commutators, okay, but it does.
Quick one.
Yeah.
Real quick in that lower Lie algebra, the order of the indices on the F, does it matter that they're a little bit?
Let me see.
Okay. Because the order changes what the number is, right? Especially if we have B and C in the commutator.
Yeah, you're right. These should actually be B, C, A.
Is it cyclic?
Yeah, it is cyclic.
Okay.
It is cyclic.
Okay, cool.
Okay, yeah, good question, good hint, great answer. Okay, now I'm going to write something. Okay, so what have we done? I'll remind you. We started with this in Lagrangian, which was invariant under global SE3 transformations. Remember, these e to the minus IQ over h bar c lambda, these are 3 by 3 matrices because the lambdas are 3 by 3 matrices. This gives you a 3 by 3 matrix acting on psi realized as a 3-component vector in red, blue, and green space. Okay? We took this thing, we replaced the normal derivative with this special covariant derivative, which we demanded this gives us this transformation law, and that told us how to transform A. There it is. So with that, the Lagrangian here with a capital D mu there is invariant, but then we want to add in the F mu nu term so that the gauge fields can propagate. Now the F mu nu term is 1/12 or 1/16 pi F mu nu, but we had to go through some work just to build F mu nu. So now that we've got an expression for F mu nu, we want to plug it in here, and this was going to give us something very interesting. Okay? So, I'm just going to release a bunch of crap. Sure, I'm going to need it later on, but that's fine. Okay, so here we go. So this is our new interpretation of F mu nu. That is, we also sum over the A index. Okay? And if we do this, this is what we're going to get. This is just the first term in parentheses is f lower mu nu, the second term in parentheses is f upper mu nu, and now I gotta multiply this bad boy out. But this is where the wonderful part of this story comes in. Multiplying this out and then recollecting terms, we end up with the following. No more good jokes?
Fourth last one's good.
They kind of sucked, but you know, I'm kind of desperate here. No, they were good. Avery, tell us another joke.
Oh, yeah, it's kind of inappropriate, but I'm going to put my quantum particle in your mom's classically forbidden region.
Hey, funny.
It's more of a threat.
It's a promise.
I guess the right word is.
Shut up, Avery, I'm done. Okay. Now, look, all I'm doing is I'm multiplying these two things out. So this is one of those things like, why is the professor doing that? Like, I could have done that. Shit, my brain works that good. Well, here's the thing. What is this? Say it again?
That's like the F mu F mu.
Yeah, this is just like U1. These are intrinsically tied to the fact that SU3 is non-abelian. They all involve the structure constants. What are the structure constants of an abelian group? They're 0. If the group's abelian, the commutator of everything is 0. That means the structure constants are all 0. So for an abelian group, all of these structure... Listen, folks, pay attention. This is cool. For an abelian group, all the structure constants are 0, so all of these terms vanish, and you just reduce to the regular old E&M abelian case. Okay? Here's the important observation, and I'm going to let Joel make it for me. What is this introducing to the theory?
Some set of interactions
Between?
all the various little parts of the 8 thing we were talking about.
Right. It's introducing interactions between the gluons themselves. What's the one thing you know about photons and electromagnetism? Do they interact with each other? No. Light doesn't interact with light. But here, gluons, I mean, this is a 3-gluon piece. This is a 4-gluon piece. This is, again, a 3-gluon piece. These are interactions of gluons with gluons. Okay? That's really cool. For example, ready for this? What do you get when you're trying to do electromagnetism and you remove all the matter and all you have left are gauge fields? Nothing very interesting because the gauge fields don't interact with each other. What happens if you take the strong interactions and you remove all of the matter fields so that you only have gauge fields left over? You still have a very interesting theory. Because the gauge particles can come out of nowhere and interact with themselves. Okay? Now, right now, this is very formal. These are going to play critical roles when we do a Feynman diagram approach to actually doing calculations, which is where we're going to turn after spring break. Okay? And then you'll really appreciate, but I mean, I'll just go ahead and give you just a quick preview of the way it works. In U1, when you want to draw a Feynman diagram, you have an electron come in, an electron go out, and it emits a photon. And we usually hook that up to another electron diagram. And this represents two electrons interacting by the exchange of a photon. And that's the electromagnetic interaction. Similarly, we can take two quarks and we can connect them via a gluon field. Okay? However, with gluons, we can do that. And we can do this. Because of this term and this term. Can you do that with photons? No. Okay. All right, so this introduces a lot of new effects. It introduces the possibility of glue balls. Okay, these are excited states of bound gluons that are forming things like atoms, but there's no matter there. It's just the messenger particles. And it also shifts, and this is something which we'll talk about later, it also shifts the nature of the strong interactions through a mechanism called confinement. And this is essentially what keeps the strong interactions from being long-range interactions like electromagnetism. It's the largest reason why the strong interactions are over very, very small distances. It's through this phenomenon called confinement, which arises because of the non-abelian nature. Now, I just want to show you a really quick way to think about these transformations, and then we'll go. There's a way to sort of think about these gluons, because right now the gluons are just these gauge fields. I don't know, it's really confusing, blah, blah, blah. There's sort of a way to think about it. So remember, psi, okay, so psi has, and I'll just write it with red, blue, and green indices. We'll skip the A because the A was a label for the space-time vector, the space-time spinor indices. But anyway, and what I want to do is I want to pick the gauge field A, which is associated with the first generator. So we'll use the first generator of SE3, which you might not remember, it's fine, but it takes that form, okay? And then all I want to do is I want to do a psi bar lambda dot A that's A1, not A prime. This is just the first generator, and I'm going to use the A that is associated with that. Okay? So let's just do this. So psi bar so those are the red, blue, and green components of psi bar. Okay? And then let's multiply this out, figure out what we get. We get psi red, psi blue, plus psi bar blue, psi red, plus psi bar green, psi green. I just multiplied it out, okay? And then if you think about it, what this thing is doing is it's basically acting in the following form. Now what do I mean by that? If I take BR bar and I act on red with it, the reds cancel and I'm just left with blue. And if I take RB bar and I act on blue with it, the blues cancel and I'm left with red. Can anybody see that? Yes? You see it, Avery?
I can't see a thing.
You need your glasses?
No, I lost them.
Okay, all right. Well, that's interesting that you come to class without your glasses.
It's not aware I can't see anything.
Okay, so look, all I'm trying to do is I'm trying to make the following observation. This is what the gluon is. These are the quarks. This is the gluon that's mediating interaction between them. The gluon is acting like a color-anti-color combination. That's all it's doing. I mean, it happens to be 1 over root 2 br bar plus rb bar. But there's a sense in which the gluons are defined as these bicolored objects. They carry one color and one anticolor, or linear combinations of color and anticolor. Okay? Which, if you think about it, kind of makes sense because they're 3 by 3 matrices in color space. All right? Does this make anybody feel a little bit better about one way to think about these gluons? It's funny, in this line right here, I've got you going, and you going, It's amazing. Yeah.
So when you say that it's like BR bar, can you sort of think of that as like a row column type designation?
I'll let you pick it out.
Okay.
You should be able to pick it out.
Okay.
All right?
Okay.
You'll be able to pick it out. Okay, but this is just kind of giving you a picture of one way to think about the gluons, is the gluons are kind of combinations of multicolored charges. Not multicolored quarks, but multicolored charges. Okay? This is going to play a fundamental role when we do Feynman diagrams for the strong interactions. Okay, because one of the important principles underlying QCD and strong interactions is the conservation of color. You can't let a color line disappear. And so labeling your gluon lines with bicolor is going to play an important role. Okay, anyway, that's it for today. Let's go home. I will see you all next Tuesday. And please be aware you've got a homework due next Thursday.
So I got an original computer and I got all the data off of the computer. So I think I'm just gonna make a cake.